Good evening, I'm Gio Almonte and today we'll be discussing some questions from Chapter 25. For first question, we have the question, for the power rating of a light bulb such as 100 watt bulb is the power it dissipates when connected across a 120 volt potential difference. What is the resistance of A, a 150 watt bulb, and B, a 60 watt bulb? And B, how much current does each bulb draw in normal use? Well, let's look at our given. So first we find that the power is 100 watts and our potential difference or voltage is 120 volts. So, as we remember, the equation for power is P is equal to V squared over R. So right now we are trying to find the resistance. So all we need to do is to transpose these equations. So we put R to the left and move P to the bottom. So we have a final equation of R is equal to V squared over P. Then all we need to do is to substitute. So 120 squared over 100 is equal to 144 ohms. Meanwhile, 120 squared over 60 is equal to 240 ohms. So now we have the first two resistances, 144 ohms for a 150 watt bulb and a 240 ohms for 60 watt bulb. Next, deriving from these equations again, we know that power is equal to I squared multiplied to R. So, to get I, all we need to do is divide P by R and square root the entire thing. So, I is equal to square root of P over R. So, looking to our equation, we have the equation of square root of 100 watts over 144 ohms, which is the resistance we got a while ago. And we end up with a current of 0.83 amperes. This is the current for this 150 watt bulb. Next, we input our second equation, which is square root of 60 watts over 240 ohms, and we end up with the answer of 0.5 ampere. This is the current for the 60 watt bulb. For our second question, we have a question. An ideal voltmeter is connected to a 2 ohm resistor and a battery with the EMF of 5 volts and an internal resistance of 0.5 ohms. As shown in this figure, what is the current in the 2 ohm resistor? What is the terminal voltage of the battery? And what is the reading on the voltmeter? And explain our answers. So first, we find out that the current is equal to 0. So why is this? So look at the question. The question says that this is not just an ordinary voltmeter. This is an ideal voltmeter, meaning that in an ideal voltmeter, resistance is actually infinite. And due to the fact that the resistance is infinite, it serves as a blockage to this current, meaning that the current cannot move under an infinite resistance. So our I is equal to 0. Next, for terminal voltage, as we know, terminal voltage is equal to the EMF minus the current multiplied to the internal resistance. However, as we know already, the current is equal to 0. So, it will become E minus 0 times R. So, as we know, the terminal voltage is equal to the EMF. And our EMF is equal to 5 volts. Finally, to explain the readings in our voltmeter, there is, based on our previous answers in A and B, we know that there is no potential drop across this circuit and that the voltage in the battery is the same as all parts of the circuit. So as we know, that means that the voltmeter will be constantly reading a reading of 5 volts. For our final question, we have this question. A ductile metal wire has resistance R. What will be the resistance of this wire in terms of R if it is stretched to 3 times its original length, assuming that the density and resistivity of the material does not change when the wire is stretched? So we are given a hint that the amount of metal does not change, so stretching out the wire will affect only its cross-sectional area. So instead of using calculations, why don't we use some illustrations? So first, what I did here is I connected 3 of these wires together. So as you can see for our first figure, we have 3 wires stacked on top of another. So imagining this as an analogy of putting 3 wires close together, we can imagine that while the length stays the same, these 3 create the cross-sectional area is multiplied by 3. So we have a size of 3 cross-sectional areas. However, if we stretch it out into 3 times its original length, this is basically the same as saying that we are splitting apart these 3 wires and connecting them from front to back. So as you can see in the second equation, what we did is we just extended it by 3 lengths, but the cross-section is equal to only 1/3 of the original cross-sectional area. So given that I said that this cross-sectional area is made out of 3 individual cross-sectional areas, 1/3 of 3 is 1. So from we can see, the longer string, the length may be 3, the smaller wire is 1. So again, I am just giving an example number, and this can be applied to multiple lengths and multiple cross-sectional areas. So we are just using 3 and 1 as a sample number so that we can easily calculate the resistance in terms of R. So, as we know, volume is equal to cross-section times length, meaning that the cross-section and length are indirectly proportional. So, as the length increases, the cross-section decreases, and as the cross-section increases, the length decreases. This is given the fact that the amount of metal does not change. If the amount of metal changes, there may be a change to the volume. However, as we can see in the question, the amount of metal is not changed. So we can follow what we said in the illustration. So again, as we know, resistance is equal to P times L over A, with P being resistivity, L being the length, and A being the surface area or cross-sectional area. So first, let us assume that for the first figure, the one where all 3 are connected to each other, L is equal to 3, representing an arbitrary length of 3, and A, which is the cross-sectional area, is equal to 3. However, after we stretched, we know that these 3 are multiplied by 3 since we're connecting it from front to back. So length of 3 plus length of 3 plus length of 3, we have an overall length of 9. However, in getting this 9, we are also taking out 1/3 of the cross-sectional area each time we're moving it from front to back. So we'll get 1/3 times 3, which is equal to 1. So now we know that the cross-sectional area is equal to 1. So this, as I said, was illustrated in our previous illustration, so you can go back to that to better understand that question. So again, we substitute. So R is equal to P times 3 over 3, with 3 representing the length and the cross-sectional area representing the other 3 representing the cross-sectional area. While for the next equation, we have R is equal to P times 9 over 1, with 9 representing the second length and 1 representing the second cross-sectional area. So after solving, we find out that when the 3 wires are put together, we have an R is equal to P. However, when they are connected in succession, we have R is equal to 9P. So from this, we can see that the resistance is actually increased as the length increases, and it actually decreases as the cross-sectional area is increased. So as we can see, we have even by lengthening this wire by a factor of 3, we're actually multiplying its resistance by a factor of 9. So thank you for joining me in this session for chapter 25. I hope you'll be able to join with me in chapter 26. Thank you.